Hello everyone, this is Exam Physics. Welcome back. A quick recap. Now VAX is always equals to VCD since they are connected together. But at now deflection, there's no current flowing through these two wires. So we might as well pretend that these two wires are not there. For this very basic circuit, VCD is obviously equals to E2 and VAX is a fraction of E1. That's why in our VCD is equals to VAX equation, we have E2 equals to the balance length, LAX, divided by the total length of the slide wire, LAB, times E1. So that's the most basic circuit. Let's move on to more complicated variants. Alright, let's start with E2 having an internal resistance small r. Now is this going to affect the balance length? Nope, because there's no current flowing in the secondary circuit. So there's no PD across the internal resistance. And therefore, VCD is still equals to E2. So our VCD is equals to VAX equation is still going to look the same. So whether there's internal resistance or not, the balance length is still the same. Alright, so how about adding an external resistance R to the secondary circuit? Clearly, current I2 is now going to flow in the secondary circuit. The current is going to flow this way in this complete loop. There's now going to be a PD across the internal resistance, and therefore VCD is no longer equals to the EMF of the battery. It's going to be equals to the terminal PD of the battery. So the VCD is equals to VAX equation is going to read like this. This is just the potential divider principle because E2 is now divided between the external resistance and the internal resistance. Since we are now trying to balance the terminal PD instead of the EMF, the balance length is going to be shorter. Okay, what's next? Now, sometimes while we are searching for the null deflection point, we may accidentally tap the jockey too near point A. Do you see the problem with that? We have basically shorted this battery. We have connected this battery with a 0 ohm wire. This is going to draw a large current and it may damage the galvanometer. So to prevent this from happening, we can add a safety resistor in series with the jockey. So even if we make the tap at the very extreme end, the current is going to be limited by this safety resistor. So how is that going to change our VCD is equals to VAX equation? Nothing. Nothing changed at all. Because remember at null deflection, there's no current flowing here. So you might as well remove this connection here. So it should be clearer to you now that there's no current flowing through RS. So there's no PD across RS, which means VCD is still equals to the terminal PD. So having this protective resistor actually is not going to affect the balance length at all. Alright, I think we can do one more. Suppose E1 is 2 volts and E2 is a miserable 0.1 volt. So the balance length is going to be very short. So it may look something like this. The balance length is very short because we have 2 volts across the entire slide wire, but we only need to balance something that's less than 0.1 volt. So what is the problem with a short balance length? That's right, we are going to measure this length using a ruler. So if this length is too short, say about 1 cm, then the percentage uncertainty caused by the resolution of the instrument is going to be substantial. We would very much prefer a longer balance length so that the percentage uncertainty is kept small. So how can we reduce VAB, the voltage across the slide wire, make it smaller? Maybe 0.2 volts would be nice, make it closer to E2. One way would be to replace this battery with one that has a lower EMF. but maybe you are too poor to buy a battery. So in that case, a resistor will be a cheaper option. By adding a resistor in series with the slide wire, VAB is no longer equals to E1. VAB is now a fraction of E1. So our VCD is equals to VAX equation now looks like this. This lump here is actually a VAB, and it's just the potential divider principle again. Because E1 is now divided between the slide wire and RP. So according to the potential divider principle, VAB is now equals to RAB, which is the resistance of the entire length of slide wire, divided by the total resistance of the driver circuit. Okay, I think that's enough for today. I hope you have realized that it's always the same story. First, we mentally disconnect the driver circuit from the secondary circuit. And then we go on to evaluate VCD and VAX, knowing that our evaluations will still be valid when we mentally reconnect the two circuits across the balanced length. This is because at null deflection, there's no current flowing in these two wires. So connecting these two wires did not change anything in the entire circuit. And then we happily equate VCD to VAX. Job done. Easy peasy. Ta-ta.